Okay, so I want to start by just mention briefly sort of motivation behind this work. So basically, so I want to start by reminding you about the Gromov program. So some of you may already know, then I apologize. So basically, so recall that if I take a finite generated group, and then we can turn the group into a metric space by consider the Cayley graph. So the Cayley graph is basically I need to take a finite generating set. Then the vertex set of the graph is just the group itself, and the edges. So two vertices are joined by an edge if the corresponding group element are differ by a generator. And then you can put a metric on the Cayley graph. You can just declaring that each edge has length 1. Then this will give you a path metric on the Cayley graph. And then the nice thing is that the different Cayley graph of the group are quasi-symmetric to each other. So basically, you see that the Cayley graph is not unique. So if I take a different generating set, then I can get a different graph, hence a different metric space. But the point is that all this metric space, they look quite similar to each other. So in the sense that they are quasi-symmetric, which I'm going to record the definition. So record that two metric space are quasi-symmetric. If first this two metric space, they so means that I have a map from the first metric space to second metric space, which satisfy the following properties. First, the matrix, the map is basically L by Lipschitz, but up to some bounded arrow A. And the second, I also require that the map is A dense. That means every point in X2 is at distance A from a point in the image. Okay, and then this basically is a sort of a coarse notion of by Lipschitz equivalence. You can understand it's just a by Lipschitz equivalence after a bounded arrow. And then it turns out that if you take a group, then take a finite generated group, then different Cayley graphs that are quasi-symmetric to each other as metric spaces. So that means every group has a well-defined quasi-symmetry type. And then we want to, and then there's this Gromov program. It's basically to classify finite generated group and metric space up to quasi-symmetry. Okay, so that's sort of the main motivation for my talk today. And then also I need to say there's another term I want to define. So we define this notion of a quasi-symmetry, but if we only require this condition A, but we don't require that this map is coarsely surjective, then this kind of map are called quasi-symmetric embedding. Okay, so now now basically the goal is to classify this metric space or finite generated group after quasi-symmetry. Then the natural question is, if I take a quasi-symmetry between two metric space, then what kind of structure are preserved by quasi-symmetry? So now I want to mention a fact that, so basically, suppose our ambient space is the hyperbolic plane. Then in this case, we have a very nice starting point to study quasi-symmetry. Basically, we know that any quasi-symmetry from the hyperbolic plane to itself is going to map geodesics to geodesics after finite Hausdorff distance. So, and also I want to say how is this work? So basically, if I take a quasi-symmetry from a space X to a space Y, there's always map a geodesic in X to something which is called a quasi-geodesic. That means the image of a quasi-metric embedding with domain being the real line. Okay, so this is just follows from the definition of quasi-symmetry. So a quasi-geodesic is mapped to a geodesic is mapped to a quasi-geodesic. And then we have the following nice Morse lemma, basically says that in hyperbolic plane, so each quasi-geodesic is finite at finite Hausdorff distance from a geodesic. So now if we put these two together, then we know that if I take a quasi-symmetry from hyperbolic plane to itself, so you take a geodesic, it's going to map to a quasi-geodesic, but the Morse lemma tells you any quasi-geodesic is actually a geodesic after finite Hausdorff distance. That's why we know the collection of geodesics are preserved after find a host of these states. That would be a very robust quasi-symmetric invariant to start with to understand the quasi-symmetries. Okay. So now, unfortunately, so this Morse lemma is so nice. But it's not true if you are not hyperbolic. So in general, for example, if you just take the Euclidean plane, then the Morse lemma is going to fail. So in general, quasi-geodesic could look like this, or also could look like something which is spirals like that. So there's no way to say that this kind of quasi-geodesic find a host of distance from a geodesic. Okay, and indeed, here also we no longer knows that a quasi-symmetry is going to send a geodesic to a geodesic up to a finite host of distance. So a quasi-symmetry, you can imagine a quasi-symmetry could take this line and bend this line in this way, or even there are more complicated quasi-symmetry from R2 to R2, which sort of map this line to something which sort of spiral around. So basically, so this geodesic behave very badly, and the quasi-symmetry if your space is not hyperbolic in general. Okay, so that means we hope to find other kind of quasi-symmetric environment if we're studying quasi-symmetry classification of spaces which are not necessarily hyperbolic. Okay, so now again, so let's look at our next example. Is going to be a product of two hyperbolic plane, and I'm going to take a quasi-symmetry from this space to itself. So now the question is, we want to sort of find some nice QI invariant. That means we want to find some nice subspace which is preserved by quasi-symmetry, or some nice subset which behave well under the quasi-symmetry. So how would I do that? So okay, so here we know that this H2 times H2 contain a lot of planes, because we can take a 9 in the first H2 and take another 9 in the second H2. So you have a lot of planes. So that means basically we should not expect that if you take a geodesic, then the image is going to be close to a geodesic, because we already seen that if you have a plane, then the sort of geodesic could bend, or could potentially bend, or there's a lot of spiraling inside a plane. Okay, so and this space has a lot of planes. Okay, so we should not expect that the quasi-symmetry image of a geodesic to be something nice. However, so the idea is that okay, so if you think about what is bad about this example, is that I have a Euclidean space sitting inside a higher dimensional Euclidean space, and this is the sort of a situation which is very flexible. So then you can bend this lower dimensional Euclidean space inside a higher dimensional Euclidean space. There's a lot of flexibility. But here, so the idea is that, so suppose I'm going to take a two-dimensional flat. So that's going to be an isometrically embedded Euclidean plane. So by flat, I mean an isometrically embedded plane. Then we know that in this space, H2 times H2, there is no three-dimensional flats. So then basically these two flats is sort of maximal flat. So you cannot find, this flat is not contained of Euclidean region of high dimension where you can bend inside. So then sort of the expectation is that maybe this kind of flat, the image and the quasi-symmetry would be something reasonable. Okay, so now we're going to ask what does the image looks like if you just take a plane, this kind of flat plane. And then so now, before I answer the question, I want to make some definitions. So I define an n-dimensional quasi-flat in a metric space to be the image of a quasi-symmetric embedding of a Euclidean space. Okay, so and basically by definition, so a quasi-symmetry is going to send a flat to a quasi-flat. So that's the main reason why we introduce this definition. Okay, and then by just from the definition, we know that the image is a quasi-flat. So now we could ask, what does a two-dimensional quasi-flat looks like? is that version for Morse lemma. Okay, so basically, we're already seeing that the Morse lemma for the hyperbolic space is basically, it says that the quasi-geodesics, which are one-dimensional quasi-flat, it says that one-dimensional quasi-flat in the hyperbolic plane is sort of close to a geodesic. And then sort of a naive analog of that would be a two-dimensional quasi-flat in, let's say, in H2 times H2, maybe that's sort of close to a two-dimensional flat. Okay, so that turns out to be not true, but there's a weaker statement which is true. Okay, so now I want to tell you, so what should be the correct version of Morse lemma for two-dimensional Morse quasi-flat? Okay, so any questions so far? Okay, so now there's no question. I'm going to continue. So before I give you the answer to this question, I need to introduce some terminology. So, okay, so now I first need to introduce the notion of cat-zero space. So that's going to be the class of space I'm going to work with. So I said a geodesic, recall that a geodesic metric space is cat-zero if triangles in Y in this metric space are thinner than those triangles in the Euclidean plane. So this is basically a sort of intuitive way to define a non-positive curvature for metric space. So what does this mean? Okay, so here's a more rigorous definition. So a metric space with geodesic means that every 2 points are joined by a geodesic. And then a triangle in a metric space is just I take PQR and I join them by a geodesic. So this is what I mean by a triangle. And then for any triangle in the metric space, on the left side, I can draw a comparison triangle on the right side. A comparison triangle is just a triangle in the Euclidean plane such that the distance between P bar Q bar equal to the distance between PQ, and similarly, the distance between these two other pair of points is going to be equal to the corresponding distance. So this is what we mean by a comparison triangle in the Euclidean plane. And then, so now I can take 2 points. On the metric space, I can take 2 points X and Y sitting in the triangle. Then I can take 2 comparison points, X bar, Y bar, such that the distance between P bar X bar is equal to the distance between PX. And similarly, P bar Y bar has the same distance as PY. Okay, so and then by saying that the triangles on the left are thinner than triangle on the right, I mean that for any 2 points X and Y, the distance between X and Y is lesser than the distance between that comparison point. Okay, so this is what I mean by triangles are thinner. Okay, so this is a very intuitive definition of non-positive curvature of metric space. And some example to have in mind is that simply connected complete Riemannian manifold with curvature less equal than 0, they're cat-zero. And all the trees are cat-zero because in a tree, the triangles are just tripod. So they're the thinnest triangle in the world. And also all the Hilbert space, so all the L2 spaces, they with the natural metric is a cat-zero space. The point is that cat-zero space allow you to treat space with singularities like trees or spaces which are infinite dimensional like a Hilbert space. Okay, so now I also want to define, there's a nice notion of boundary for cat-zero space. So, okay, so the definition as follows. So I take a base point in Y, and then the boundary, the T's boundary of Y as a set is just a collection of geodesic rays emanating from P. Okay, each boundary point corresponding to a geodesic rays starting from P. And then there is also a metric on the T's boundary. So the metric is given by sort of the angle, some kind of angle between these two rays. So, okay, so here's a picture. So let's say I take these two rays. On the left side, I take 2 rays in the cat-zero space. So now I want to define the angle between these 2 rays. What do? I'm going to take 2 points X1 and X2. And I'm going to form a comparison triangle, this P bar, X bar, 1, X2 bar, which is a comparison triangle for this triangle P, X1, X2. And this comparison triangle live inside the Euclidean plane. And then, so now we will see there's an angle of the comparison triangle at P bar. So this we call the comparison angle. So now I define the asymptotic angle between these 2 rays to be the limit of comparison angle as X1 and x2 sliding going as x1 and x2 go to infinity along this geodesic rays. Okay, so it turns out that the limit always exists. Okay, so this is how I define the symmetrical angle between the two rays. So basically, I just let x1 and x2 go to infinity, and then look at the limit of the comparison triangle. So that's going to be the asymptotic angle I'm going to define. And that's going to induce a distance on the collection of geodesic rays eliminated from P. So that's going to be the T's boundary. So this boundary is this set equipped with this metric, which induced by this asymptotic angle. Okay. So any questions about the definition? Okay, so now I'm going to continue. So now with this definition in mind, so I want to go back to give a description of what is a two-dimensional quasi-flat in H2 times H2. So it's more complicated. It's not just a flat. So now, but using T's boundary, we have a sort of precise characterization of what are this quasi-flat. Okay, so now I take X to be the product to hyperbolic plane, and I take the T's boundary of X1. So it turns out that the T's boundary of X1 is just a bunch of points. And it actually the metric I just defined from the asymptotic angle actually gives the discrete topology on this set. Okay, so so the T's boundary of X is just the complete bipartite graph on the T's boundary of X1 and the T's boundary of X2. So that means I view the T's boundary of X1 as just a discrete set, the T's boundary of X2 as just a discrete set. So recall that means that a collection of geodesic rays in X1, and this means the collection of geodesic rays in X2 starting from some base point. And the T's boundary of X is the completely bipartite graph. That's basically a graph whose vertex set are T's boundary of X1 and the T's boundary of X2. And basically there's an edge between any point, any vertex in T's boundary of X1 and any point in T's boundary of X2. So this is what I mean by a complete bipartite graph. Okay. So now, what are the edges? So basically, each edge is going to connect. Okay, so this is what I just said. So each edge connect a point in the T's boundary of X1 to the T's boundary of X2. And how do we see it geometrically? So we already know by definition that each point in the T's boundary corresponding to a ray. And then so now so sigma I, so it's a T's boundary in xi, so that's corresponding to a ray in xi. And then this edge basically corresponding to this quarter planes R1 times R2 in X. Okay, so I have a ray in X1 and I have a ray in X2, and then this R1 times R2 sit inside X1 times X2. That's going to give you a quarter plane, and that's corresponding to an edge on the T's boundary. And then, so now, if I take a cycle in this complete bipartite graph, okay, so by cycle, it just means it's just a collection of edge which sort of close up, okay? So, and that's going to give you, because the cycle is made of a sequence of edges, and each edge is going to correspond to the quarter planes. So that means each cycle is going to give you a collection of quarter planes in X of this form R1 times R2 that are assembled in a cyclic fashion. So basically, the picture you should have in mind is that I have a collection of quarter planes that glue along each other along the boundary in a cyclic way. So, and it turns out that the union of these quarter planes is a two-dimensional quasi-flat. So this is essentially, there's a theorem saying that any two-dimensional quasi-flat is more or less, it basically comes from this construction up to find Hausdorff distance. So now you see that it's not true that any two-dimensional quasi-flat is Hausdorff close to a flat. So basically, so the two-dimensional quasi-flat is host of close to a flat if only if there's a 4 quarter plane. But a priori, a quasi-flat could have 6 quarter planes or 8 quarter planes. That's basically corresponding to the number of edges in a cycle in a complete bipartite graph. Okay, so you could have cycles made of arbitrarily large number of edges. So thus you have 2-dimensional quasi-flat made of arbitrarily large number of quarter planes. Okay, so now this tells you, okay, so the most naive expectation that the quasi-flat are close to flat are not true. However, we still know there's some kind of structure. So the quasi-flat is more or less a union of quarter planes. So this actually tells you that the 2-dimensional quasi-flat are actually host of close to a geodesic cone. So they are straight because each quarter plane is basically a geodesic cone. By geodesic cone, I just means a union of geodesics. And then each quarter plane is definitely a geodesic cone. And then so now you're just gluing a bunch of geodesic cones, you still get a geodesic cone. Okay, so this basically means that the 2-dimensional quasi-flat, they're sort of straight. We cannot see this kind of crazy bending or spiraling we've seen in sort of in the case of a 1-dimensional quasi-flat in a 2-dimensional plane. So that does not happen. So they're still straight. So they are not housed of close to flat, but they are straight in the sense that they're housed of close to geodesic cones. Okay. So and then so now this kind of picture generalized to more general cat-zero space. So I'm going to take a co-compact cat-zero space. So this if you're not familiar with cat-zero space, you can just think about Riemannian manifold with curvature less or equal than 0. Okay, so the universal simply connected Riemannian manifold, complete curvature less or equal than 0. Okay, and then co-compact just means that the space modeled by its isometric group is compact. And then I define a flat in X is top rank if we cannot find a flat whose dimension is bigger than F. Okay, so basically it's for example in H2 times H2, a top rank flat has to have dimension 2 because we cannot find a flat with dimension 3. And on the hyperbolic space, a top rank flat has dimension 1 because we cannot find a flat with dimension 2. Okay, so this would mean we have top rank. So this is basically this sort of flat which has sort of maximal flat. Okay, and then so now and it's not hard to believe based on what we discussed so far that flat or quasi-flat of top dimension or top rank, so they behave nicely under quasi-symmetry. So the rough reason is that so now we are in a non-positive curved space. So that means the space is sort of mixture of 0 curvature, which is like this flat or quasi-flat, and also a negative curvature. So but if you take a flat which is a top rank, so that's sort of like a maximal Euclidean region, and then that kind of region intuitive that may behave more rigid under the quasi-symmetry. So that's sort of the intuition that why there's no bending or spiraling. And then it's actually a recent theorem by Kleiner and S that top rank quasi-flat in co-compact cat-zero space are sublinearly close to geodesic cones. So okay, so I'm going to explain what does mean by sublinearly close later. Okay, so let's leave this term undefined. This basically says that that they looks quite like geodesic cones. They are straight. Okay, so okay, so now and this actually is a good starting point to study quasi-symmetry. So now I want to going back to my initial motivation. So I said that all of these are motivated by the Gromov's program for to sort of classify quasi-symmetry, classify finite generated group and the matrix space up to quasi-symmetry. How does this all things are related? So basically, what we discussed so far actually give rise to a general strategy to attach attacking Gromov's program for non-positive curved spaces and groups. Okay, so basically it goes through the following two steps. So the first step is basically, so we already seen that the image of top rank flats, the top rank quasi-flats, and these quasi-flats behave nicely, so they're quite straight. So this suggests that we can use our basic invariant as these top rank flats and quasi-flats. And the first step is to understand the structure of top rank flats and quasi-flats. And then usually the quasi-flats is going to have some kind of intrinsic combinatorial structure come from the ambient space. So we already seen in the case of quasi-flat in H2 times H2, the quasi-flat has a two-dimensional quasi-flat has a combinatorial structure, which is basically a union of these quarter planes. And this sort of combinatorial structure is compatible with the product structure of the ambient space, which is H2 times H2. So this is what I mean by combinatorial structure inherited from an ambient space. Okay, so that would be a specific example. And then so to prove this kind of result, usually one would start with some nice geometric properties of the top rank quasi-flats, like they're straight, they're not something crazy. So this allows us to sort of discover this kind of combinatorial structure. Okay, so now from here we know that this top dimensional top rank flats or quasi-flats, they have some nice structure. And then we also know that these top rank flats or quasi-flats, they are quasi-symmetrically invariant, because a quasi-symmetry, by definition, a quasi-symmetry is going to send a quasi-flat to a quasi-flat. So that means the quasi-symmetry also going to preserve the intersection pattern of how this quasi-flat fit together with each other. Okay, so that means the information we have is sort of, we have the combinatorics of the intersection pattern of this top dimensional flats or quasi-flat is preserved, and the quasi-symmetry. We also know that this quasi-flat itself has an underlying combinatorial structure, and all this combinatorial structure are preserved and the quasi-symmetry. So this gives us a lot of information about what kind of thing are invariant under the quasi-symmetry. And then so this basically reduce the study of quasi-symmetry to a sort of a problem of understanding the combinatorics of intersection pattern of certain collection of flats or quasi-flats. Okay, and in some specific case, this combinatorics could be understood, and that's going to lead to a quasi-symmetry classification or quasi-symmetry rigidity result. Okay, so I want to say that there are several very fundamental theorems was proved using this strategy. So one of the theorem is the following. So basically, proof using this strategy is this following nice theorem by Kleiner and S in 1990s. So they proved that X and Y to be irreducible symmetric space of non-compact type, and suppose they have higher rank, then these two spaces are quasi-symmetric if and only if they're isometric. Okay. Okay, so this is just this is sort of a discussion of how we use these top rank flats or quasi-flats to prove nice QI quasi-symmetry classification result. Okay, so now, so I should also point out that there are limitations to this kind of method. So because you see that this method, it only tells you that the flats which are top rank are nice, behave nicely under the quasi-symmetry. So we already seen before that if you take a flat which is not top rank, like a 9 inside a plane, then in general it's very hard to say what's the image. So the image could be a huge mass. Okay, so now, and this leads us to the following question. So okay, so in general, would be enough if we just consider top rank flats or quasi-flats. So it turns out if you just care about symmetric space, then that's enough. Okay, or if you only care about mapping class group, that's enough. or Teichmüller space, that's also enough. But for more general spaces, so there may be a lot of information hidden in this lower dimensional part of the space, which is not captured by the top rank flats and quasi-flats. So that means if you use this strategy, just focus yourself on the combinatorials or the information come from the top rank flats or quasi-flats, then you might lose track of a big chunk of your space. Okay, and then a simple example to have in mind is the following. So I take X and Y to be space obtained by just gluing a bunch of flat torus of different dimension. That's the asymmetrical unknown subtori. So okay, and then let's so let's suppose we glue it in some correct way. So there are various gluing theorems tells you if you glue in a certain way, then you will know that the universal cover is cat 0. Okay, so then suppose we're gluing in some way such that the universal cover is cat 0. Okay, so now let's say, so suppose I want to ask so if I take these two space, that's x2 and y2, then are they quasi-symmetric or not? Okay, or and then so now, okay, so you are saying, okay, so what we can do is we can apply the previous strategy. So we can try to look at top dimensional flat. So in this case, the top dimensional flat come from the top dimensional tori. But in our space, so there are a lot of but the problem is that our space is made of tori of various dimension, and there could be lots of lower dimensional tori, which sort of leads to flats, and we have no control on that flats. So it looks like from this kind of examples, we can only have top rank flats, have only control on the top rank flats and their intersections. We don't have control on those flats which come from lower dimensional tori. Okay, so and on the other hand, maybe so this lower dimensional tori maybe consists of large part of your space. So so that leads to a substantial loss of information. Okay. So now how should we sort of save this strategy? So basically we said that the strategy in the previous slides only treats top rank flats, but somehow our intuition is that why the top rank flats are good, because they are not contained in some high dimensional flats. So maybe we don't really need the flats to be top dimensional. Maybe you just take any flats which are not contained in high dimensional flats, like a lift of a maximal torus. They will behave well under the quasi-symmetry. There may not be any bending and spiraling. So that's sort of what we're trying to generalize. Okay, so we want to sort of look at sort of flats which are not containing high dimensional flats, but they may not be top dimensional. Okay, so now so naively, okay, so let's take X to be a cat 0 space. So and I take a flat which is not containing a high dimensional flats or even a high dimensional half flat. Okay, so now naively one can ask whether these flats are good or not. So unfortunately, okay, so I take a quasi-symmetry. So should we expect the quasi-symmetry image of this such kind of maximal flat to be straight in any sense? Actually, the answer is no. So it's sort of more subtle than that. So here's an example to have in mind. So what is my X? X is just I take a 9 and I glue a bunch of cube, a bunch of larger and larger cube to the 9 in this fashion. So now you see that okay, clearly this 9 is not containing any two-dimensional flats or even two-dimensional half flats, but we see larger and larger chunk of 9 are actually contained in this kind of large Euclidean boxes. And you could imagine that a lot of bad things could happen in these Euclidean boxes. So inside this sort of larger and larger boxes, so there could be a lot of bending or spiraling. Okay, so that's why we should not hope that the image of this 9, okay, So we should not hope that the image of this line is housed close to a geodesic, okay, because of this sort of larger and larger Euclidean region, which is sort of attached to this line, okay. So that means this question is a little bit subtle. So, so the vague intuition is that if you have something which is maximal, then it should be rigid. But this example shows that it's actually not the case. Okay, so if we just say naively maximality, if we just try to characterize naively maximality, we're going to fail. Okay, so now to give the correct characterization, I want to discuss another example. So now our goal now is to at least try to characterize one-dimensional maximal flat or quasi-flat correctly. So want to define the correct sense of maxima such that it really guarantees that the quasi-symmetry image is straight. Okay. So now I want to look at another example, which is basically I take a wedge of a torus and a circle, and then I take the universal cover. And the universal cover is going to be something called a tree of flats, because this torus is going to lift this flats, and this circles is going to lift to these 9 segments, which sort of connecting these flats in a tree-like fashion. So this is what the universal cover looks like. And then, so now, so we know that, we already know that if you take a geodesic inside a flat, then we should not hope the quasi-symmetry image to be nice. So now let's try to look at a geodesic which sort of avoid these flats, so which are transverse to all flats. More precisely, I demand that I take a geodesic that there's a uniform upper bound on how long they stay inside one particular flat. And it turns out that this kind of quasi-geodesics are quite nice. So they have a name, they called Morse Quasiflats. And then there is a version of Morse lemma for this kind of geodesic. So as long as they avoid all the flats, then we know that this Morse quasi-geodesics are actually housed close to geodesic. So this is sort of a generalization we're seeing in the hyperbolic plane. And as a consequence, we know that the quasi-symmetry is going to preserve this Morse geodesic. In this context, just those geodesic which there's a uniform upper bound on how long they stay in one particular flat. Okay, so then the quasi-symmetry is going to map this kind of geodesics to geodesics after finding Hausdorff distance. Okay, so it seems that this is the kind of quasi-geodesic we're looking for. Okay, so now I want to, okay, so now this actually gives rise to sort of a correct characterization of what we really want. Okay, so I want to, so that's one particular characterization of the Morse quasi-geodesic is in terms of the divergence. So okay, so basically it says the following. So I take so this is a geodesic or quasi-geodesic. So now we say the quasi-geodesic has superlinear divergence if the following thing holds true. So let's try to connect 2 points on this geodesic. By avoiding this arbor, and so that means you have to sort of go around this arbor, and then so this and then we demand that whenever you're trying to join 2 points at a distance 2r, where avoid the arbor central at that middle point, then such path is going to have length which is superlinear in Q. Okay, so I want to say that the length of R divided by R go to infinity as R go to infinity. So this is what I mean by superlinear divergence. Okay. And then, so clearly this is true if you take a geodesic line in a hyperbolic plane, because if this is a picture in the hyperbolic plane, then if you go around this ball, then the length has to be at least the e to the r. That's clearly superlinear in R. Okay. So now so this is this will be one definition of the Morse quasi-flat quasi-geodesic. This is what happened in one-dimensional situation. So now what I want to do next is to generalize this definition to higher dimensional situation. Okay, so now you could already imagine what I'm going to do. Instead of consider geodesic, I'm going to consider flat. Instead of consider 2 points, which is like can be thought as S0, I can consider a sphere of radius r. I'm trying to fill in a sphere of radius r outside some ball and want to declare that the sphere has to have volume which is large enough. Okay, so now let me set up this rigorously. Okay, so first let's look at what's going to happen in the Euclidean space. So I take a co-dimension 1 flat in the Euclidean space. Okay, so here's the picture. And then, so now I'm trying to, so this is a 2 flat in a 3 space. So now I take a R sphere inside the 2 flat. So I want to fill this R sphere, which is just a circle. I want to fill this circle by some chain. Okay, so suppose a sphere while avoiding the R over 2 ball. And then we know that the volume of this hemisphere is sort of to the order R squared. So if you're doing it in Rn, this is Rn minus 1 inside Rn, then the volume of this hemisphere is going to be of the order R to the n minus 1. Okay, so this is a sort of, if you're trying to fill in a sphere outside a large ball, in the Euclidean space, and you should get one of this order, R to the n minus 1. And then, so now our definition of Morse quasi-flat is that I want to demand that if you're trying to do the same thing for Morse quasi-flat, then it's going to be harder to fill in R squared in a Morse quasi-flat by chance in the space, avoiding the R over 2 ball. Harder in the sense that you need more volume to fill in the R sphere compared to this volume R to the n minus 1. Okay, so it's again sort of we're trying to compare to what happened in Euclidean space, and we want to say here it's harder to fill. Okay, so here is the definition. Okay, so now I take X to be some metric space and Q be a n-dimensional quasi-flat. Okay. And for simplicity, let's just assume phi is actually continuous or even L Lipschitz. So now what we want to do is, okay, so now I take this quasi-flat and I take a n-1 dimensional sphere. Okay, so here instead of a sphere, I want to sort of consider more general object like just some n-1 dimensional homology class, which is non-trivial in this En remove the R ball centered at X. Okay, so for example, a sphere would be a particular such cycle, but I want to consider all such Lipschitz cycles. So now, since I'm passing to Lipschitz cycles, then they may have multiplicity. So then we also want to assume the multiplicity is not too high. So why this mass bound? So we want to say the volume of this Lipschitz cycle is sort of comparable to R to the n minus 1. So again, you should think about if you take a sphere inside En of radius R, then the volume of the sphere is sort of comparable to R to the n minus 1. And this is what it roughly says. So this sort of generalized sphere, but it does not have to be sphere. It could be any Lipschitz cycle with a reasonable volume bound. Okay. And then, so now we want to say that if you're trying to fill in this Lipschitz cycle by another chain, which are avoiding some R ball. Okay, so but I want to consider R over D, but at the moment, for simplicity, I just you can just imagine a case you take D equal to 1. So now I have a Lipschitz cycle outside the R ball. I want to fill in the Lipschitz cycle by a chain which is also outside the R ball. Okay. And then the claim is that then I would require that this cycle is harder to fill compared to the Euclidean situation, in the sense that the volume of this chain which fill in the cycle has to be a function times r to the n, where this function go to infinity as r go to infinity. Okay, so and then this is the definition of Morse quasi-flat. So whenever you have a flat, so that means whenever you have an n-dimensional quasi-flat, such that if you're trying to fill in the spheres outside the R ball, the filling volume is larger than what you see in the Euclidean space. So in the Euclidean space, if you want to do that, then that's going to be of all the R to the n. So here I want to say that it's harder to fill. That means I want the volume of this Lipschitz chain to be delta of R times R to the n, where delta R go to infinity as R go to infinity. So this is our way of saying it's harder to fill, okay, compared to the Euclidean situation. Then this kind of divergent property is going to characterize Morse quasi-flat. Okay, so in other words, a Morse quasi-flat are exactly those quasi-flat where if you're trying to fill in cycles in the quasi-flat outside a large ball, then it's harder to fill compared to the Euclidean situation. Okay, so that's the definition. So is any questions about this definition? Okay, then I will continue. So this is the definition of Morse quasi-flat, and this is sort of the correct way of saying this maximal. Okay, so we want to say it through this sort of measure the divergence where we compare to the Euclidean situation. Okay, so now I want to give you some examples of Morse quasi-flat. So first, the Morse quasigeodesic would be a one-dimensional Morse quasi-flat, and then we'll talk about this top rank quasi-flats. They are again Morse quasi-flat. So this sort of generalized top rank quasi-flat, but they don't have to top rank. Okay, and also they behave well under product. So product Morse quasi-flat are again Morse quasi-flat. So the proof of this is actually not too hard because we set up the definition of Morse quasi-flat in a homological way. So the proof is just an application of some version of the Quinn-Ness formula. Okay, and then another situation is that if I have a, let's say, a Z2 and Z3 are migrate unknown Z, then this copy of Z2 is going to be a Morse quasi-flat. Okay, so notice that this Z2 is not top rank because the rank of the space is actually 3. Okay, and there's also a higher dimensional analog of a well-known criterion by Bellman in the case of dimension 1. Okay, so previously we say that if you have a flat which are sort of not contain a high dimensional flat, then we will sort of have this naive hope that that flat is going to be sort of nice, and then it turns out that that's going to be true if the flat is actually co-compact. So if I take a co-compact flat in a proper cat-zero space X, so a flat is co-compact, that means there's an isometry. So basically there's isometry, there's subgroup of an isometry group of X which leave F invariant and act co-compact on F. Okay, this is what I mean by a co-compact flat. Okay, and then if this F does not bound the isometrically embedded Euclidean half flat of one dimensional higher, then F is a Morse flat. Okay, and I should say that there's a related notion called Morse subset, which was introduced by several other authors. So Morse quasi-flat is in generally not a Morse subset in the sense of Geneva and Argentova, Kashin, Gruber, and Huang. Okay, so this is just a clarification on the terminology. So now I also want to give you some examples with group theory. So since we're saying in the beginning that we want to use this to study quasi-symmetry classification of groups. So what happened in the case of groups? So now I take a group and I take a free abelian group. We say the free abelian group is the highest if the group does not have a finite index subgroup which is contained in an abelian group of higher rank. So the highest abelian group is sort of a a group which is maximal in an algebraic sense. And then we ask whether this kind of abelian subgroup, are they also Morse quasi-flat? And then it turns out that this is true in certain cases. So we know that highest abelian subgroup in right-angle Artin group, right-angle coxed group, or more generally in any virtually compact special group, they are actually Morse quasi-flat. Also, we know that highest abelian subgroup in mapping class group of surfaces, they are also Morse quasi-flat. So in certain case, this Morse quasi-flat can be seen algebraically. Okay. So now I want to go to the more sort of the main point of my talk is going to be this asymptotic conicality. So basically, it tells you that this sort of Morse quasi-flat, they're really nice, so they are straight in the following sense. Okay, so now again, so I'm going to take X in the as a K0 space, and I take a base point, and again I take the T's boundary of X. Recall that the points in the T's boundary are just geodesic rays emanating from some base point, and then the T's boundary is equipped with some metric which come from the asymptotic angle between these two geodesic rays. And then the main thing roughly is that if I take a Morse quasi-flat, then the Morse quasi-flat has a well-defined boundary, which is a subset of the T's boundary. And the Morse quasi-flat is actually sublinearly close to a cone of the T's boundary. Okay, so what do I mean by cone over the subset? Because any subset, so every point in the T's boundary corresponding to a geodesic ray. And then this cone over the subset is just the union of geodesic rays emanating from P corresponding to points in the subset. So this is what I mean by a cone. Okay, so now I'm going to state the theorem in a more rigorous way. So I take an n-dimensional Morse quasi-flat, and then let's say X is, sorry, so there's an important assumption that here we have to assume X is K0. Okay, and then basically, then we know that there's a subset of the T's boundary with the following property. Okay, so basically, so all what I want to say here is that if you look at the cone over the subset, so if you take a subset of the T's boundary, that's going to give you a geodesic cone, which is a union of rays corresponding to points in the subset. And all what I want to say over here is
we cannot hear you. Jing.
Maybe he's disconnected.
Probably.
He's coming back. Yeah. Okay.
Hello.
Okay.
Yes, we can hear you now.
Yeah, sorry. So for some reason, yeah. So the Zoom suddenly stopped. So.
Okay.
Yeah. So I'm going to share my screen again. Sorry. Yeah. Okay. So yeah. So sorry for the interruption. So let's continue. Okay. So basically here I basically want to say that any Morse quasi-geodesic is going to be sublinearly close to this geodesic cone. Okay, so more precisely, I can try to look at the portion of the quasi-flat inside a large ball. So imagine that this BPR is a large ball, R is a large radial center at P. So I look at the portion of the quasi-flat in a large ball, and I'm going to compare this to the portion of the geodesic cone inside this large ball. then the Hausdorff distance between these two sets are very small compared to this scale R. Okay, so this R is the scale I'm taking. Okay, so this is what this formula is saying. So and then this delta R is going to be a small number. So when R is large, then this delta R is actually really small. Okay, so this is what I mean by sublinearly close. Okay, so you could naturally ask, can we actually prove that the Q and the cone are actually Hausdorff close? Well, this we don't know the answer. So we know that they're actually Hausdorff close in some very specific case, but we don't know what happened in general. So in general, the best thing we can show is that the cone and the quasiflats are sublinearly close, and this turns out to be already good enough for us to deduce some quasi-symmetry rigidity result. Okay, so now I should also say that this boundary set, so this is going to be some subset of the T boundary, is actually represents a homology class. So we can think about in the case of H2 times H2, in that case, the boundary of Q is just a cycle in this bipartite graph, and that's indeed represent a homology class. And this is also true in general. So this set, this boundary of the Q is not just a set. This also has a structure of a cycle. It's a sort of a cycle at infinity. Okay. So now I want to mention that some application of this result to quasi-symmetry rigidity. So we can it allows us to deduce some nice result about quasi-symmetry classification of graph product. So recall that. So I want to first recall the notion of graph product. So I take gamma to a finite simplicial graph, and then basically for each vertex of the graph, I'm going to associate a vertex group GV, and I define the graph product over this graph gamma. It's going to be the following group. So I first start with the free product of all the vertex group GV, and then I'm going to add a commutator between two vertex groups. So I demand GV is going to commute with GW if V and W are joined by edge in gamma. Okay. So one special case of this, which is quite extensively studied in geometric group theory, is that if the vertex group is Z, then you got the right angle Artin group with defining graph gamma. So now, so there's a previous definition due to Barcelona, Kleiner, and Sagiv. So they will study certain collection of right-angle Artin group with a specific class of graph. So this is what they call atomic. Okay, so they define a graph to be atomic if it has no valence 1 vertex, has girth bigger than 5, and no separate closed star. So that means if you take the closed star of any vertex, then it does not separate the graph. So for example, there's plenty of graphs satisfy this condition, and you can take an angle with n bigger than 5. That's going to be a very simple example of an atomic graph. And then what Barcelona, Kleiner, Sagiv proved, they proved the following very nice quasi-symmetry classification for right-angle Artin group. So they say that if I take two atomic graph, then two right-angle Artin group, they're quasi-symmetric if and only if they're isomorphic. Okay, so now what we want to do is so notice that this theorem by Barcelona, Kleiner, Sagiv only consider right-angle Artin group. That means they only concerns the graph product where the underlying vertex group are Z's. And it's natural to ask whether there's a generalization of this group where you can consider more complicated vertex group. And then this is what we can get by studying Morse Quasiflat. So okay, so we basically prove an analog statement, but we are now for a much more wide class of vertex group. So again, I take two atomic graph, and I take two graph product where the vertex group are rank 1 right angle coxed group or Artin group. So the vertex group could be arbitrary rank 1 right angle coxed group or Artin group. And then we know that these two groups are quasi-symmetric if only if first the graph are the same, and second the corresponding vertex group are quasi-symmetric to each other. Okay, so I think, yeah, I just realized that I'm running out of time, so I think I should just stop here, and thank you very much for your attention.